In industrial automation systems, understanding network hierarchy is crucial for efficient and secure operations. Two fundamental components within this hierarchy are the plant bus and terminal bus, which play distinct roles in the communication architecture of systems such as ICS, SCA, DA, and DCS. These network layers help organize data flow and control, ensuring that information moves seamlessly between devices and management systems. Standards like IEC 61850, the Purdue model, and ISA 95 provide frameworks for structuring these networks, promoting interoperability and reliability. By referencing these standards, organizations can design automation systems that are both scalable and resilient. This foundational knowledge sets the stage for exploring how each layer contributes to overall system performance and safety. The plant bus serves as the central communication backbone for an entire facility, enabling seamless data exchange across various systems and departments. It handles high-level traffic, such as supervisory control commands, status updates, and process information, ensuring that critical data flows efficiently throughout the plant. Common protocols used on the plant bus include Ethernet/IP, Modbus TCP, and PROFINET, which provide robust and standardized communication. Devices connected to the plant bus often include distributed control systems, human-machine interfaces, engineering workstations, and enterprise resource planning systems. By linking these diverse components, the plant bus facilitates system-wide coordination, integration, and real-time decision-making. This unified approach helps optimize operations, improve reliability, and support advanced automation strategies across the facility. The terminal bus serves as the backbone of localized communication within industrial environments, enabling real-time control and seamless device interfacing. It operates using specialized protocols designed to handle various types of traffic, such as sensor data, actuator commands, and status updates. Devices commonly connected to the terminal bus include programmable logic controllers, sensors, actuators, and human-machine interfaces. By facilitating deterministic and reliable data exchange, the terminal bus ensures that operations on the factory floor remain synchronized and efficient. Its architecture prioritizes low latency and high reliability, which are essential for maintaining precise control over automated processes. As a result, the terminal bus plays a critical role in supporting the demanding requirements of modern manufacturing systems. Plant bus and terminal bus are two distinct network layers commonly found in industrial automation systems. The plant bus operates at a broader scope, connecting various controllers, servers, and devices throughout the facility, and is responsible for managing large-scale data exchange and coordination. In contrast, the terminal bus functions at a more localized level, linking field devices such as sensors and actuators directly to controllers. The requirements for plant bus typically include higher bandwidth, robust security, and support for complex protocols, while terminal bus emphasizes reliability, real-time performance, and simplicity. Typical topologies for plant bus are often hierarchical or ring-based, supporting redundancy and scalability, whereas terminal bus usually adopts star or daisy chain configurations for straightforward device integration. These two layers interact by allowing the terminal bus to collect and transmit real-time data from field devices to the plant bus, which then aggregates, processes, and distributes information across the wider network. Together, they create a seamless data flow, ensuring efficient operation and monitoring throughout the industrial environment. Network segmentation plays a crucial role in automation architecture by isolating critical systems and minimizing exposure to potential threats. By dividing networks into distinct zones, organizations can better control data flow, and prevent unauthorized access. Protecting the terminal bus from unnecessary traffic is especially important, as this component often handles sensitive operational commands and data exchanges. Excessive or irrelevant traffic can lead to performance degradation, increased risk of cyber attacks, and potential disruptions in industrial processes. Ensuring that only authorized communications reach the terminal bus helps maintain system reliability and safeguards essential operations. Ultimately, robust segmentation and security measures are foundational for achieving both safety and efficiency in modern industrial environments. Terminal bus, the last mile for real-time control. Field controller. Plant bus, the information backbone for plant management. Controller system-wide applications. Understanding this hierarchy is fundamental to designing secure, efficient, and reliable industrial automation systems. It's also why firewalls and network segmentation are crucial. You must protect the real-time terminal bus from unnecessary traffic originating on the plant bus or higher corporate networks.